just because we've hit 5 o'clock, and then my camera, of course, plays up. So while we're waiting on a few more people maybe to log on, I'll just introduce myself. My name is Willem Vervoort. I'm an associate professor of hydrology and catchment management at the University of Sydney. My colleague here, Pedro Leitao Chambel, am I saying that correct, Pedro? Is in Portugal and connecting up from Portugal, and is with one of our partners in this project with Hidromod. And he will do part of the presentation, and I will give part of the presentation. Welcome everybody. Welcome on this late afternoon in Sydney, and wherever you are in Europe or in Australia, connecting up to this first webinar that we're trying to give to tell a little bit about our project, which is funded under the European Horizon 22 program under grant agreement number 870344. So as I was posting in the chat, we will collect your questions in the chat as well, so we can answer later on if we don't get to answering your question during the webinar. Okay, so maybe without further ado, given that we're having a few stories here, I'll start. I wanted to first give a few slides just to introduce the project. So WaterSENSE is a project called which is trying to make, or our slogan is making sense of the water value chain in Australia. The project's running from January 2020 up to 2023. We've been already going for almost 2 years, and it's focused specifically on the use of Copernicus data on delivering information about the water value chain in Australia. So what some of the goals that we have are, the objectives that we have are to create a modular water monitoring system capable of dealing with a large variety of data sets at different time and space scales, to develop some algorithms that enhance and integrate the Copernicus data and models, and have models in situ data to quantify water availability and water use. Research to develop some integrated calibration and validation method for WaterSENSE, and develop and demonstrate the value of WaterSENSE in close cooperation with prospective end users. Now, just to build on that, I forgot to say that WaterSENSE is a small to medium enterprise driven program, research and action program. And so our partners are a group of companies in Europe and in Australia. eLeaf, Hydrologic, Hidromod, Hydrometeo, and HCP are all companies in Europe. And Water Technology is a company that is in Melbourne, and University of Sydney is the research partner university. And finally, so that we are developing some business cases with flexible subscription models to look at different markets and customers, including a roadmap for global uptake. So our initial demonstration is Australia, of course, partly because Australia signed up to the International Copernicus Cooperation Arrangement. And also we have quite a bit of interesting problems, of course, in Australia that we can focus on and that we can deal with. Our initial focus area is actually in the Namoi catchment, but we have a few more areas that we want to focus on. So the concept is that we developed this toolbox, which delivers both the monitoring and the management in terms of the water that we're interested in trying to work with, and that integrates the Earth observation data from Copernicus. So if you want to connect with us, and I'll show this slide later on when we finish as well, here are some details from some of the people that you might want to connect with. So with that, I'll just switch over to my presentation. So this presentation is showing some of the research that we've been doing at the University of Sydney that works. And so Ignacio Fuentes has been the main person developing this work together with Jose Padarian, who is a colleague, and myself. And so we're trying to look at how we fuse data sets for to actually downscale soil moisture information, and using some deep learning approaches through that. So essentially, there are multiple ways to predict soil moisture. When we're talking about soil moisture, we have, of course, several of the microwave soil moisture remote sensing data sets, such as things like the SMOS and SMAP and different other data sets that are available online. We have optical and thermal sensors that we could use for that, and there are some relationships like the TOTREM and OPTREM approaches that are related to that, where they're trying to figure out the soil moisture from things like NDVI. And then finally, there are people who are using some downscaling and looking at downscaling from remotely sensed soil moisture down to, of course, in situ measurements and try and make comparisons. And finally, we have things like machine learning that we can now apply to try and deliver this kind of soil moisture observations down to actually finer scales that we might want to use this data at the local scale. So when we review some of the current methods in terms of soil moisture predictions, we're finding that a lot of the work that currently is going on, particularly in the area of machine learning, is that it's mainly for, and in terms of satellite observations, that it's mainly focused on surface soil moisture. So a lot of people are looking at 0 to 10 centimeters as their observation area. I'm just going to get another pointer. So you have a laser pointer. Right. The other problem that we have, and we have that same problem in this project, is that there is limited availability of actually existing soil moisture observations, and a lot of that soil moisture observation can also be a bit uncertain. So it's quite difficult to kind of actually build a model that's accurate enough because of the paucity of the actual data that's available. So what we do find is that when you look at some of the results that already exist, is that there is some questionable performance when you try to extrapolate to conditions outside the actual original data set. And that's also, of course, an issue that we are trying to deal with. And then a lot of research has been focused so far on agricultural land use. So what we're presenting here is not particularly the end all for this prediction, but at least it's a step in a direction where we think there is future opportunity as well. So the aims of this study are to try and develop a soil moisture product that can actually predict at the field scale, and that can also predict different soil depths. We wanted to develop for that some downscaling methods, models, based on basically land use classes to kind of improve the predictions that we currently are doing. And then to do that, we also wanted to look at, okay, what actually are important covariates? So if we're trying to make these downscaling models and we're trying to do these predictions, what covariates can be actually helpful and what kind of covariates can be useful to try and actually make better predictions of soil moisture? And then finally, to at least make an attempt at predicting, evaluating the prediction uncertainty. And there is more work to be done in that area. So we needed to work with some reference data. This is some typical reference data for Australia that we have available. There is slightly more data available in other areas, and there is actually a lot more data available in more private repositories. But in terms of the publicly available data sets, AusNet and AusFlux are probably the two data sets that have been used the most. And this gives you an understanding of the distribution of that data across Australia. And you can see that it's very sparse in many, many places, right? So that both of these data sets are based on TDR based soil moisture observations. So there are new data sets that involve capacitance probes, and that is definitely an option that we can look at. And there are also the Cosmos data set that is based on the cosmic radiation data that we can use for soil moisture. So this just gives you some overview. So the AusNet stations are focused and concentrated in the Murrumbidgee catchment, and they're from an earlier research project that are still operating, and they're very handy because they're quite concentrated and very local. And then there are the AusFlux towers, which are more distributed across Australia and have been used, for example, also for the most recent CMRSET data set developed by TURN and CSIRO. and have just been released. So the covariates that we looked at are the Sentinel-1, because we wanted to use Copernicus data, and particularly we're looking at the backscatter intensity and the RSSM, which here gives you an understanding of that basically looks at dry and wet and the relative soil moisture index. We looked at MODIS, surface reflectance bands, land surface temperature, and land cover. And we looked at some soil properties. So we used the SLGA. Now there is the SLGA is model data for the soil landscape data for Australia. We looked at the model data for clay, for soil organic carbon, and the available water capacity. And it's soil properties from 0 to 60 centimeters depth. We're going to go down to 60 centimeters depth as well. Then we use the ACLM data set for land use, which is another, broad scale data set for land use in Australia. And then we looked at lagged variables, things like surface and subsurface soil moisture from the NASA USDA SMAP data set. And we also used the CHIRPS data set, the rainfall data set in that. So we essentially built two models. The first model is a typical surface soil moisture model. So we used all these different data sets that we had developed, or the covariates, and we use them as input in basically a simple neural network with a bunch of hidden layers, and we're then predicting the soil moisture 0 to 10 centimeters. So this is more a classical approach to soil moisture neural network modeling, that machine learning modeling that we can see in other areas as well. The second approach that we did was we used some deep learning. So we used some memory models, components within within a neural network, and particularly then to model both the soil moisture at 0 to 30 centimeters, but also at 30 to 60 centimeters. So here we want to jointly predict both the surface and the subsurface layers within a neural network that includes a deep learning memory part input, right? And again, we're using this similar kind of time series data and the other layers that we've got involved in there. We then, to kind of, like we said, trying to get an understanding of the influence of the different covariates and understanding the covariates, we used Shapley's additive explanations, trying to explain the prediction of an instance by computing the contribution of each of the features. So in this case, the covariates to the prediction, right? So we're trying to interpret that. And then for uncertainty, we only looked at predictive uncertainty. So essentially, we're using the variance of the cross-validation results. So we basically did cross-validation for all these sites. And what we did was leave one out, cross-validation. So we left one site out. So we actually left one site out rather than actually do just a data point out. Right, so it's important to realize that we're doing, we're basically leaving one site out for when we develop the model, and then we're predicting that independent site. So that's that's a bit more rigorous than if you would select a subset of the data and then making the prediction over a subset of the data. And the reason why we did that is because, of course, there's autocorrelation within the data, and we didn't want to. We wanted to make sure that we actually, so you're actually over predicting your performance if you're just doing a leave one out validation. We wanted to do a more stringent one where we leave a whole site out. Okay, so here is some example of the SMAP performance against the reference data. So if we're just looking at the SMAP, we can see what we predict. These are basically looking at root mean square error. We're looking at the mean average error, and we're looking at correlations. So, for some sites, you actually get some reasonable correlations and low errors, particularly for the surface moisture. But when you're looking at the subsurface, that blows out quite quickly. And that's typically what you see with current soil moisture products. So when we then look at our downscaling models, and we're looking at the 0 to 10, the 0 to 30, and the 0 to 30 to 60, you can see for the 0 to 10, we are similar to the SMAP. We're maybe a little bit better, get a little bit better correlation. But again, there's quite a bit of variation, of course, by site. And then for the 0 to 30, we improve quite considerably, and particularly in the errors compared to the straight SMAP data. And we also get some better correlation. So we improve our correlation relative to what we would do by just using SMAP. And here is some, as a test, we thought we'd also look at some specific sites. So here's a couple of the specific sites that are from the Oz Flux data set. Or one is, this is actually OzNet, that's an OzNet, and then there's a couple of Oz Flux data sets. And we also plot as the background the benchmark aura model. So we looked at what 5 kilometer grid we were in for the aura model, and we looked at the soil moisture for that aura model, and then also looked at the prediction for that. So you can see we're doing reasonably well at all these sites in terms of the prediction of soil moisture at the local scale. So we feel fairly confident that we're actually doing a reasonable job at predicting soil moisture at locations. If you look at specific land uses, you can see that there is a bit of variation across land uses. Partly that, of course, is driven by the number of stations that we have. So, you know, if we have a lot more stations, we can tighten up that actual correlation, and we can get a better performance. While if you're looking at the correlation, for example, at the Savannah shrublands, where we only have 4 sites, it's, you know, correlations are much lower. Similarly, if you start looking at depth, you can see of course we have fewer stations, because there's fewer stations where we have both depths. So that makes it a bit harder to look at, but still, you know, we get fairly tight root mean square errors and mean average errors, if you think about it in terms of what we're trying to do in terms of predicting soil moisture. So, you know, it's small percentages relative to what we observe. Of course, there are certain land uses that clearly stand out as being worse than the others, and there are certain land uses that perform much better in terms of irrigated pasture sites and things like that. If you then start looking at how we interpret that, and we look at the different characteristics, different covariates, one of the interesting things is that if you like looking at the combined depth predictions, right, which is the surface and subsurface modeling, you can see that the importance of the clay really improves. And you can also see that the land use, or no, not improves, but the actual soil properties, soil characteristics increase. So there's more importance of the soil properties and the land use characteristics when you're looking at the predictions in depth relative to when you're looking at the predictions just on the surface, where basically the actual SMAP observations are the most important ones for making that prediction, and which is logically that's what you're going to have see there. So just as an example, we thought we'd show just how it performs when you zoom in to a certain location. So in this case, it's a location in the Nemoy catchment. And if you look at the drought index for that location, we have a very wet period here in 2016, 2017, and we have a very, very dry period. It was 2019, 2020. So if you then look at the evolution of the soil moisture, you can see how it nicely maps that as it changes in time. And you can also see the uncertainty related to that and how that relates to the land uses and how it relates to certain features within the landscape. So the uncertainty definitely is mappable in terms of the product that we have here. And you can get these nice contrasts in the actual soil moisture predictions. And the ranges are reasonable. That's not a strange range. That's not, you know, like it's blowing out to much higher. But you can see that for certain areas, the uncertainty is quite high, still quite high. This is just showing it for the combined surface and subsurface mapping, same kind of thing. Now we have the time in the vertical column. We can see the vertical column times, and we can see the uncertainties related to that. And here we can see, you know, this is for the subsurface, this is for the surface. And again, the uncertainty in the subsurface is slightly higher relative to the uncertainty in the surface predictions. And overall, the uncertainty is higher relative than if we're just looking at the surface prediction, 0 to 10 centimeters. So, of course, this is, as I said, this is mostly a research in progress, and there is more that we could do and are interested in. One of the things is, of course, we would love to have more reference data. So we'd like to have more data available so we can actually test the model better and we can develop the model further. We also would like to, investigate whether there are other neural network architectures that we can work on that and can develop that. And we've just put in a proposal to try and see if we can develop some more Bayesian, stricter developments of the uncertainty quantification to actually look through, use that within the network and get better estimates of the uncertainty than what we're getting here, where we're just simply using it predictive uncertainty across the cross-validation. Doing a more formal estimation of uncertainty would probably be better. So we looked also at the International Soil Moisture Network. Again, we'd like to see more data. We really, reference data is clearly a difficulty. The other thing we're finding, even with the TDI network, there is some variation in terms of the installation and some variation in terms of the actual data collection, and that can also be important. And similarly, when we look at some of the data that's available in the capacitance probe area, there's quite a bit of variation across those, and it would be nice to also include that uncertainty in the actual observed data within the actual model, but we haven't got to that point. Ignacio, this is his email if you want to get in contact with him. That's my email at Sydney if you're interested in that as well. So I think I've mostly stuck to time. In fact, I've gone a bit fast, but that's okay. So if I've gone too fast, if there are any questions, then I'm happy to answer those. Maybe I'll stop sharing and just look for if there is on the chat or somewhere else, if people are interested in asking questions on this. If not, you can also ask them later. Otherwise, I will just hand over to Pedro and give Pedro a chance to tell his story.
Okay, thank you. I will try to do a presentation as good as yours. It won't be easy work, but I will try. So now for something completely different. So still about soil moisture, but now the numerical modeling perspective. So I started working with this some 20 or more years ago, and I'm going to start with where I started from when we started the development of the model, the results of the model that I'm going to show you here in the University of Lisbon. So this is relevant because it has consequences for everything that I'm going to show afterwards. Basically, what this is saying is that we are going to model this in finite volumes. That we work with models that solve the continuity equation, which in the end altogether solve the Richards equation. And all those terms that you see here are important. Those first three terms are important because they are related with how water gets into the soil, how water can come up from the aquifer into the soil. So basically the K's are the conductivity, the phi is the matrix potential, theta is the volumetric water content, and all these things determine how water flows in the soil and how water goes into the soil. And of course, gravity also has an important role in how water flows in the soil. So here just a small thing, which is in fact, by changing a little bit the equation, you have the saturated flow, and in this case you have to replace the phi by an h, which means basically that you have to take into consideration the water height to be able to know what is the matrix potential in each cell. Here also, it is only relevant to say this, to say that to solve unsaturated or saturated is more or less the same thing. In our model, it is just one domain, the unsaturated one, and the equation is mostly the same with some few adaptations. There are many numerical models available, so I just put, well, some that are more known to me, but they are so many that I would, they have many. So I just mentioned here some plot scale models, Hydros 1D, Aquacrop, RZWQM, Moidland, and watershed models, which in fact also solve the soil moisture, which is Moidland, SWOT, Mike Shea, and many others. So this is the model that I'm going to talk to you about mostly, and I'm just going to talk about it because it was the one where I started developing, yeah, but again, all the models solve more or less the same thing. And as I was telling you, so in Moidland we solve a 3D domain, which includes the aquifer and the vadose zone. And here in this image, what you can see, so there are many arrows that want to show you that Moidland model is a model that is integrated. So it integrates the river and the runoff. So it calculates at a watershed scale, but we can also look at it as just a plot scale model to be able to simulate a plot or a paddock, I think, as you say there in Australia. And what this image shows you is that in the porous media, the flows can happen in the vertical direction, but also in the horizontal direction. On the horizontal direction typically is when the soil is already saturated, though unsaturated soil can also flow on the horizontal direction if you have big matrix potentials differences. So it solves the 3D Richards equation, the 2D Darcy equation, and includes infiltration, evapotranspiration, and precipitation variable in space and time, well, and many other interesting stuff. And it uses finite volume and variable time step. This was one of the first examples I did. So this slide, it might be already 20 years old. I don't remember exactly. And since this was in the start of development of the model, that shows the effect and importance of the type of soil. So on the right side, you can see the experiment that shows how in a sand layer, the experiment has a layer of sand on the left and a layer of clay on the right. And you can see how water progresses depending on the layer. So the clay layer, you have a more distributed front, and in the sand, you see that the water goes through without spreading too much. And so this is just to show the two models reproducing the same effect. So this is what we want to do with models, try to reproduce what is happening in the reality. Another example could be macropores. So if you have a macropore, it behaves more or less like you have in the images below. So in the beginning, the water goes rapidly down into the end of the macropore and starts spreading to the walls of the macropore in the soil. And then with time, water starts to spread more and more. And again, you can see here the model representing these same processes. And then you can get more, you can start to zoom out. And in here, you can see an experiment that was done here in the south of Portugal, where you can see there on the left, these cubes of soil was to avoid any kind of horizontal flows and to be able to control the experiment. And so you can do these very detailed experiments. On the right, what you can see is the evolution of water in these cubes of soil. And so you can see that this rainbow scale here, water content varies from 0.2 to 0.39, and the errors is the water flowing up and down as a function of the irrigation that was being applied. And so you can see the zero flux plane going up and down depending on the irrigation and the evapotranspiration processes. What is the zero flux is basically where you have where the flux never go upward, let's say, from that point on. As you can see here, the zero flux is progressing, and there is a point where it inverts again to go up. Why is this important? Because this is the point below which there is no water going up for contributing for evapotranspiration. And you can see clearly also here the differences in the type of soil. So this is a kind of result that you can, in the bottom right, you can see the time going by. And you can see the same results in a different graph, which is what you have here on the right, which is a TZ graph. And this is interesting because you can see everything that you are seeing in the middle animation, you can see just in a fixed image. And so you can see on the bottom, you can see the time. Sorry, in the X direction, you can see the time. In the Y direction, you can see the water content, the depth, sorry. And so it is clear. So the colors, again, it is water content, that in this case, they are varying almost from 0 to 0.45. And you can see the irrigation applied. You can see the water that is, whenever this becomes blue, it means that the water is flowing down the soil profile. And you can see also clearly the different soil properties. That's why you have these discontinuities here, because the soil properties change in this soil. So we have 3 layers of soil. So again, this is very detailed simulation, but it shows you the processes that are happening. So the washing, and it's important for salinity of the soil to know how much water is washing down. You can also see here on the surface, this red, it means the amount of evaporation that you are getting from the surface layer. And you can see, of course, in the rest of the profile, you can see the water that is being available for the roots. So the root zone is the important part. That's where farmers want to keep the water, not below here. And then you can see the winter event. So all this bluish, it's the raining event. So in Portugal, the raining events are not many. When they happen, they are relevant. So that's why we depend very much on reservoirs, a little bit like Australia, to store the water for agriculture. Okay, so another example related with irrigation system. You can see here, so this is an irrigation system, drip irrigation system, where the drip is under the ground. This has some advantages, this system, but also some operational difficulties. But this was to see and to understand how water was flowing in around a system like this, and also in this case to see how the nitrates were flowing in a system like this. So again, detailed simulation, and then we can start zoom out again, and we can do a plot scale simulation. And here what you can see again is water content, and I'm trying to pretty much focus on water content, on soil moisture. And so you can see a field. This is a field of corn, so you can see the evolution of the water content on a 2D, so the surface, and then on the left you can see here a cross section in this area where you can see the variation in depth of the soil moisture. So you can see that in the bottom part, you have a relatively shallow aquifer, which is keeping this lower part mostly saturated, and then on the surface you can see the variation of the soil moisture, and you can see how variable it is, the soil moisture in this field. And then we can zoom out again, and we can go for integration of the soil moisture with everything else. And so here it's an example where we are associating everything, where we are putting soil moisture together with the river flow, where we are having interaction between the soil and the river, and where we have also the flow in the river contribute to the coastal area. And here we have another model, also MOID, but for coastal areas. So this is MOID land, this is MOID water. And by the way, the name MOID is from the Portuguese Modelo Hidrodynamic, which is hydrodynamic model. And so we have MOID water for coastal areas and water masses, and MOID land for interior waters. And so you can see on this scale, this gray scale, you can see the soil moisture varying depending on the precipitation events. And also, of course, depending on the precipitation event and the interaction between the soil and the runoff and the river, you can have the water flowing into the river and eventually from the river into the soil. And here again, the higher the flow, the lower the salinity, and here the scale is the blue scale is a scale of salinity. You can see the higher the flow, the lower the salinity. Okay, but this was just to show an example of the integration of all of this, that's where this becomes complicated, time-consuming in terms of computation, and this is where we as a company start thinking if we should use these models, or eventually should use more complicated ones, if we should simplify some of the processes that we are simulating, remove some processes. This is something that we have to wait with based on the data we have and the objectives of our clients. So should we consider simpler models? Yes, in some cases. And just to present you, so what I shown you is a model that has, so MOID, it has, depending on the situations, you can have more processing time if you have periods of very big changes, either a lot of evapotranspiration or a lot of evaporation in a very dry soil, or for example, if you have periods of very high precipitation and you start to flood. And so it can happen, of course, you can go around all these things, but it can happen that it becomes time consuming. It can happen. So sometimes it is also useful to look at simpler models. So SWOT, I put here as an example of a simpler model in terms of soil modeling. So basically it uses the very simple concept of the wilting point, field capacity, and saturation, where the field capacity is the water that, and this is it's a simplification, because in fact field capacity depends on the depth of the aquifer, and so field capacity is when the water does not flow. Saturation, between saturation and field capacity, water flows according with gravitation, with the gravity and the saturated conductivity. And down here you have the wilting point, where there is no water for the roots. Here there is water available for plants to grow. So a very simple model like this can also be used, and it's easier to compute. So it takes into consideration, as I said, the content of the soil and the saturated conductivity. and also it has some lateral flow depending on the inclination, but as you can see, very simple equations with no special numerical problems associated with it. And you can generate again similar results. In this case, it is a watershed model, period. It's not like wildland where we can use it almost as a laboratory where we can take out parts of it and simulate it separately. So it is a fully watershed model where you can see here on the left the river flows, in this case already applied to Namoi watershed, and on the right you can see the soil moisture varying for each one of the sub-basins. So what about Australia and WaterSENSE? Now going to the interesting part. As I have shown you very, let's say, very zoomed in, maybe results, but the idea here was mostly to get your attention to how it is possible for us to simulate more detailed processes in the soil, because they have some complications. But there is, of course, the uncertainties with which we live. So the first ones are the plant, the surface water or soil, and how much we are transpirating, how much we are evaporating, the separation between these two, and sometimes even summing the two of them. This is something, one of the uncertainties that we expect to be able to have more control in WaterSENSE, because we are going to have evapotranspiration estimated by satellite. This will be made by is being made by ELIF. We are going to have the precipitation measured by radar, which gives us a more detailed precipitation. And to know, and this is a challenge, to know how much water it is being irrigated and precipitated into a field is a challenge. And for us, it's needed to estimate the soil moisture. Of course, there are many other challenges, namely the root, how root it is distributed in the soil, to know the depth of the groundwater, because you can have capillary rise if the groundwater is closer to the surface. And of course, there are other things like the roughness of the terrain, root distribution, porous media depth. Sometimes just to know what is the porous media depth, it is a challenge. So there is a lot of uncertainty. So our big hope here in Australian WaterSENSE is that we are going to have some data that will allow us to tackle some of these uncertainties. Okay, so some simulations for Australia. What we tried to do was to gather rainfall, weather data, and some KC values, which is basically the crop coefficients that allow us to go from reference evapotranspiration to the cultural evapotranspiration. And with the radar of precipitation that we have for Namoi, we can have this kind of results. So this is a 1 kilometer grid model, benefiting from the 1 kilometer grid precipitation. And the interesting thing of this model is that you can see that the footprint of the precipitation that you can see is clearly variable in space. This footprint is being left in the soil, and shows how important it is to use to have good precipitation data. Down here you can see our results for the same periods, and you can see that it also has some variability but it is not the one related with this kind of precipitation. Then we have here another simulation, but unfortunately, as was William saying, we have few data to validate all this. So here the idea of this slide was to show you that we can now move for a more local simulation, and here we can go for the plot scale simulation. And in this case, we were testing for a farm, two different setups to simulate soil moisture. In this case, for 1 point, in fact, for one plot. And we can see that depending on the precipitation that we are using, and we were using 2 precipitation stations, we can have completely different soil moisture. Now, what I was starting to say, so we have very few data, so we use also the Yanku site as William to try to validate what we were doing using this OSFlux data, and we managed to have some comparisons between what we were modeling and what is in the reality. So we can still see here some differences, but we can also see that there are some places where the model is representing quite well. In this case, the 3 centimeters depth, and in this case, it is the 15 centimeters depth. And finally, and so basically what we are looking for in this kind of results is to see if we have the recession curve right, if we are getting the peaks right, the big peaks, the continuum peaks. This is what we try to achieve. Okay, so next steps is testing my other input data. So like improving the KCs, which is let's say a simplification for us to take into consideration what is the plants that we are using in our system, and with that estimate the ATC. Of course, to have a crop detection system is important because these KCs are important for us to estimate the amount of water that we are evapotranspirating. And this is the tests that we'll hope will improve or will reduce our uncertainty in what relates with our with the plant growth and the evapotranspiration. Compare results with satellite-derived soil moisture, kind of soil moisture that Willem showed to us, and make some operational example for Australia. Right now we have some examples running already, and we are producing everyday soil moisture estimations using our model. So the operational system, it is working, but we still have to validate and to improve the data, and this is what we have been doing. And as soon as we have reasonable results, we are ready to put this to work for some clients that could have interest on this type of results. So I think this is what I had to show you. I hope it was at the same time interesting and that could bring some questions up right now.
Pedro, there were 2 questions on the chat, which I thought I've tried to answer partly, but so one question was about the depth of the soils, how you work that out, and I answered that. For Australia, we would use the SLGA, but you might be able to answer that more broadly, how you would figure out the depth of soil, you know, that you make a decision on in terms of your model. Sorry, you're muted.
Sorry for that. The depth of soil, it is something that we, it's, as I said, it's one of the uncertainties. It seems like a simple thing, but it's a kind of data that is normally is not guaranteedly around. And because there are two worlds, the world of the agronomists and the world of the geologists. And the agronomists, they are normally worried about 1 meter of soil, and sometimes the soil has more than 1 meter. And so there is this area between the geologists and the agronomists, which it is not known, and sometimes it's also including the soil depth. And so it is something that in the end it is not easy to obtain, and sometimes we have even to use it as a calibration parameter, because of course we would prefer to have perfect soil maps that would give us the depth of the soil. When we have it, we use it. If we don't have it, we use it as a calibration parameter. And I use the opportunity also to answer another question that I'm seeing here: if moist land and moist water, if they are used commonly. Well, yes, please, the only thing I can tell you, yeah, they are used by our company, they are used by Bentley, they are used in the academic world, and so they are also commercially used. But yeah, so to answer fast to your question, of course, if you have more questions, if you ask me if you can start running it tomorrow, of course, I'm not going to lie you that they are very easy, because well, there is some specificities, but yeah, they are relatively easy to use, and so yeah, they are available in the, and they have the advantage that the source code is completely available in GitHub, and you can see what is coded there. This is one advantage. The disadvantage is that the interface issue is something that has some difficulties. There is some interfaces, but well, yeah, but we are happy for people to use it. Just a small comment. All the people that we use this here in Hidromod, in Bentley, and in other companies, we all came from the same research group in Lisbon, and that's why we are all using it. But it is used all over the world. If you go and see, there is papers from people from many other groups.
Thank you. Are there any other questions? I'm just madly trying to type in also our email addresses into the chat, so we can send that or have that recorded as well. I just need to get Pedro's, and then I'll be done.
Can I just add something else to the soil depth?
Yes.
There is another important thing, which is also the root depth, because, and sometimes the two are mixed, but they are not necessarily mixed, because you can have roots that go much lower than what it is typical considered the soil depth. And so the root depth is also relevant. They should be the two associated, the soil depth and the root depth. But what we know in reality, for example, we are here in Portugal, a typical tree here in Portugal, which is cork tree. Portugal is the biggest exporter of cork, and this tree, the roots go very low down into the aquifer. So they have some big shooting. I don't know if this is the right word in English. They go very well down, and they maintain the tree in the most dry periods. And so this is to say that it is not completely obvious where the water is coming from for the evapotranspiration, and this is the issue.
There's another question for you, which is more about urban water management. Whether any of these models have been used in leak detection for water mains. Definitely not SWOT. I don't think it has been. But,
right now we have moist land so it is coupled with models like SWIM. So you are able to this, I think, it does not answer any of these models being used in leak detection of water mains or wastewater mains. What
so
is
more urban, more urban. So a more urban application. So a water
what is
line,
yeah.
a water line. So a pipe,
yeah.
Water pipes.
Yeah. So we are simulating that with using SWIM. So we have swim inside the mowed land, and it is able to get water from the pipes, let's say. And this is, I'm an agronomist, so this is something that it's not of, well, it has some interest to me, but, and so we are simulating basically in urban catchments, we are simulating floods, and we are using swim for the, to simulate the pipes, let's say. I don't know exactly the right words in English, but we are doing that. So coupling this swim model, which is a reference for these pipe models.
Okay, are there any other questions? Because otherwise I will just remind you all that we're having another set. We're hoping to have another webinar in November, and it will be later in the evening to make sure that also our European people can join in, because otherwise it would be too early. So for Australia, it would be later in the evening, would be probably at 7 p.m. Because we'll be going to daylight saving here in Eastern Australia, and we want to be able to accommodate our European partners as well. Are there any questions? Further questions? And the other thing I can mention is that we also intend to have a workshop at the MOTSIM 2021 conference in Sydney in early December. And we will be linking up, looks like we will be linking up with the other Horizon 2020 project run where the University of New South Wales and University of Melbourne are involved as well. So we will be informing you about that on our LinkedIn page and on our Twitter page on that. And there will be a workshop there as well. Otherwise, if you have any questions, you also have our, let me see, there was some more in the chat. Yep, okay, just some presentations, some thank yous, that's always good. But otherwise, if you have any questions, feel free to contact us. We're more than happy to answer more questions. I'll post this recording also on the LinkedIn page, so it should be accessible for people as well. Thank you, Pedro, for your contribution. And then I think with that, we have stayed on time, which is good. And we'll close the session here, and thank you all for attending, and we'll hope to see you soon again for our next presentation.
Okay, thank you very much all.
Thank you.
Okay, bye here from Lisbon. Bye.
Bye.